You know where break is. Have you seen the gigantic cow?
Welcome back to NE 630 nuclear reactor theory. So last time we discussed the diffusion length, and we showed that the diffusion length is 1/6 the average of the square of the Crookes flight distance. And we also discussed how to calculate the diffusion length using the sigma Byle experiment. So today we will continue defining the migration length. Then we will move on to solving the diffusion equation in a multiplying medium. So the last couple of lectures was just the solution of the diffusion equation in non-multiplying medium. Today will be the first lecture for solving the diffusion equation in a multiplying medium. But before I will start, I will just show you hints about solving one of the homework problem, because I got a couple of questions regarding the solution of the fraction of neutrons that will moderate or reduce the energy below certain energy A. So the equation that you will be using is the probability that the neutron starting with energy E will go after one single collision to energy E prime is just 1 over 1 minus alpha multiplied by E. So the probability is not a function of the final energy. It's only a function of the initial energy. So if you plot the probability B of E goes to E prime versus E prime, you will notice that it is a constant value and ranges from E to alpha E. So this is the initial energy, this is the final energy, but in between those two limits, it does not depend on the energy E, and this probability is just 1 over 1 minus alpha multiplied by E. And we drove this relation in the lecture here several lectures ago, and we stated that this probability has this form once the cross-section is isotropic in the center of mass, and we cancel sigma scattering as a function of energy, or theta from upstairs was the sigma scattering downstairs, and we reach it to this one. Okay, this just gives you the probability that the neutron after one collision will go to energy E prime. But this is not what I asked in the problem. I asked, okay, if you have an energy E, what's the minimum energy that you will be going to? Alpha A. After a single collision, this is the minimum. You cannot go below alpha A. Yes? So if I asked you, okay, here is an energy E1, and let's say you are coming, some of the neutron after one collision will go up to energy here, maybe after one collision you go up to energy here, maybe you will go up to here, or maybe after one collision you will go here, or one collision will bring you directly to alpha E. So there is lots of probabilities, or lots of chances that you might get to here, but you cannot go below alpha E. The probability that you go below alpha E is 0. To go below alpha E is 0. So I asked you, what's the probability, or what's the number of neutrons, the fraction of the neutrons that will go below 5.5 MeV. So 0.5 MeV, let's say that this is E1 is 0.5 MeV and E initial is 1 MeV. So I asked you how many neutrons go below 0.5 MeV. So all what you want to do is to give me what's the number of neutrons that will go below 5 MeV. So you will just integrate this. I will not tell you how to integrate. I will not show you anything. I'm just giving you a hint. You have to integrate this over whatever. I do not know what's the limits here, and then divide by the integration from here to here. But the integration from here to here is what? is 1, because 100% you will be, if you make an interaction, a single interaction, you will be there. So it is just this divided by 1, which is this. So you will integrate over this between alpha E and E1, and then use whatever alpha for whatever material. Of course, you have E1 is 0.5 MeV, and E is 1 MeV, and you will integrate over E prime, then you will eliminate E prime, and this is how to solve the equation. So let's start with the migration length. So we defined last time that the diffusion length or diffusion area is just L square, and we showed that L square is nothing more than 1/6 R square average. And R square average here, this is the distance from the moment the neutron will be thermal. So the neutron is thermal here, start to be thermal here, make several collision in the thermal energy region. Then after those several collisions, it get absorbed here. So this is the crow flight distance, and the average of this, if you take the average squared, so 1/6 of this average of the square is just the diffusion area. So now this is defined for the thermal energy. So if the neutron is generated at the fission energy, which is, what's the average energy for the neutrons coming from fission? It's 1.98 MeV. So E average is almost 2 MeV. So it's 1.98 MeV for uranium-235. So the neutron will be born, let's say, with an average energy 2 MeV, starts slowing down until it reaches to 1 electron volt, which is the cutoff for the thermal energy region. Then in the thermal energy region, start diffusing inside the moderator, for example, in the reactor. So while it is diffusing, it will make frequent collisions until it gets absorbed. So if you take the crow flight distance and then square it and take the average for this square, this will give you the diffusion length or the diffusion area. Take the square of this will give you the diffusion length. So this is defined for the thermal energy region. For the fast energy region, while the neutron is generated here with 2 MeV, it's now in this area here, or in this energy bin here between the 1 electron volt and 0. This is the thermal energy region. So usually we call it here thermalization. The neutron is thermalizing with the media, but here the neutron is moderation or slowing down. So while you are here, you are slowing down or moderation. So you are slowing down and reducing your energy or moderating while you are here. Once you reach here, you got to the thermal energy region, then you are thermalizing your energy. You equate your energy or homogenize your energy with the medium itself. So in this energy region, if the neutron is here from fission, so it's born here at fission, and then start making frequent collisions, for example, until it reaches to the thermal energy region. Then here the energy became thermal. So this R here is similar to this, but this R is completely different from this R. This is for the thermal energy region, this is for the fast energy region. Now we can define a new parameter called tau, and tau is 1/6 R square average, but this is in the fast in the fast energy region, and this one in the thermal energy region. And this tau is called the Fermi age. So Fermi age is defined as 1/6 the Crookes flight distance, the average of the square Crookes flight distance that the neutron will take from the moment it is born as a fast neutron until the moment it will get into the thermal energy region. So this is what we call the Fermi age. So now the migration area, is defined as m, and it is equal to L squared plus tau squared. So this is just m is nothing more than 1/6 r squared average for the thermal plus r squared average for the fast. So, and again, this is called migration area, and the migration length is just the square root of m. It's called migration length, and it is again L squared plus tau squared plus tau. Sorry, this is just tau. So tau is equal to this, not tau squared. There is no tau squared. So it's L squared plus tau. So this is just to define what we mean by the diffusion area. Now, let's change gears and move to how to solve the diffusion equation in a multiplying medium as opposed to the last couple of lectures, how to solve it in non-multiplying medium. So, diffusion equation in multiplying medium. What do you think the changes will be? What do you think the diffusion equation? What's the diffusion equation? 1 over. Come on, guys. I do not want you to look at the book. Just memorize it. So this is the time-dependent term. We have a source term plus nu sigma fission term minus sigma absorption term plus nabla square phi term. Yes, guys, this is the diffusion equation. Sources and sinks equal to time rate of change. Okay, now, if I want to solve this equation, first of all, I will set the source, external source, to be 0. And then I will try to look for boundary and initial condition. So what is the boundary condition if we are looking for, let's say, a slab geometry? I want to solve this for a slab, for example. So this is A, and this is A extrapolated, and this is minus A, and this is minus A extrapolated, and this is 0. Now, before the boundary condition and the initial condition, I will assume this is what type of equation. This equation is what type of equation? Come on, guys.
Continuity?
No. What type of, is it what? Linear, differential, algebraic, what type of equation? Differential equation. Is it ordinary or partial? Why? Because I have, what?
Dependence is not on one parameter.
So I have time and space. So now, one of the methods that we discussed last time is the method of separation of what? separation of variables. So I can say that the flux here will take certain shape, and this certain shape will change with time. So I will have two independent functions. One is a function of space, and the other one is a function of what? Of time. So if I make this, I can say phi of r and time t, space r and time t, is nothing more than psi as a function of r multiplied by capital T as a function of t. So I can write the flux like this. The boundary condition here is just the flux at the boundary, which is A extrapolated. If we are talking about one dimension and the x space, for example, x domain. So phi at x, A extrapolated, and time at any time is equal to what? 0. And phi, this is the boundary condition. What is the initial condition?
That time is 0.
Phi at any r and time equal to 0 is equal to what? Phi naught, the flux at the initial. Then when you do this and take this equation and substitute here, what you will get is the following. You will get psi of r divided by velocity dt by dt equal to dt of t nabla square psi of r minus sigma absorption psi of r t of t plus nu sigma fission psi of r t of t. If you just divide by psi and t in both direction, you will get 1 over v 1 over t dt by dt equal to d nabla square psi of r minus sigma absorption plus nu sigma fission and this would be over psi here, and then if you rearrange, this will give you 1 over t dt by dt is equal to velocity v divided by psi divided by this d nabla square psi plus nu sigma fission minus sigma absorption psi equal to each other. Yes? So you have a function of time which is totally independent from a function of r, and some derivatives of this function equal to some derivatives of the other function. So this means that this function or this variation here of the function is the same like this variation of this function. So this means that this is equal to a constant and this is equal to a same constant. Yes? So in this case I would call this constants minus lambda. Then when you try to solve, the first equation will be 1 over t dt by dt equal to minus lambda, and this will give you the solution t equal to t naught e to the power of minus lambda t. And where t naught is the initial, t naught is equal t at t equal to 0. What about the other equation? V d nabla square psi plus nu sigma fission minus sigma absorption multiplied by psi equal to negative lambda multiplied by psi. So for this equation, we are seeking a solution in the form nabla square psi plus b square psi equal to 0. Somebody will say why? Because if you just divide by v here, so this will give you lambda over v, and then divide by d, you will get d here, and there is no d here, and then you can get this one here, so you will take psi as a common factor, so you will get nu sigma fission minus sigma absorption over d plus lambda over v. All this is constant, so you will call it b square. Okay guys, so just showing to you that we are seeking a solution in the form of nabla square psi plus b square psi equal to 0. What's this? What type of equation?
The second order.
homogeneous.
Yeah, this types of equation is called eigenvalue problem. Why it is eigenvalue problem? Because it is in the form of some operator A operated over a function psi will give you some lambda multiplied by the same function psi, where the operator here is just nabla square psi is equal to negative b square psi. So A, the operator that you apply on the function, is just what? Nabla square, and lambda is just what? Negative b square. Yes guys? So this is just you apply an operator over a function, and this function is called the eigenvectors. And the lambdas are calling what? Eigenvalues. So you have an eigenvectors and eigen what? Eigenvalues. So our goal is to calculate what are the eigenvalues and what are the corresponding eigenvectors or eigenfunctions. Okay guys? Yes?
Can you explain again, going from the function before the eigenvalue?
This one?
Yeah, down to the next.
I said that if you just rearrange this, you will obtain nabla square psi. Just divide by all terms by vd. So you will isolate nabla square psi plus this term is constant, mu sigma phi minus sigma absorption is constant, and this term is constant, eigenvalues is constant. So just when you bring minus lambda psi in this direction and you take psi as a common, you will have some constant multiplied by psi, which is b squared psi. Then once you rearrange, this type of equation is called eigenvalue problem. So the goal for calculating this eigenvalue problem is it has certain types, certain procedure to calculate the eigenvalue problem or to solve the eigenvalue problem. So how to solve this eigenvalue problem? Sorry, I make this. So how to solve this eigenvalue problem is we will try to solve it in 1D space, where we will assume that we have a slab reactor and there is a fissile material inside this reactor, and let's see how to solve it. It's very easy guys. If you remember, the equation is nabla square psi plus b square psi is equal to 0. By the way, this equation, they sometimes call it reactor equation. When we have psi as the flux, we call it reactor equation. So now, in one dimension, this will be what? d2 psi by what?
dx squared.
X squared plus b squared psi equal to what? 0. This is a very simple equation. So this is what? What's the solution for this equation? This is what, if you look at this solution of this equation, this is just said psi double dot equal to negative b squared psi. What's this? What's this equation in physics? Huh?
Simple harmonic.
Cerebral harmonic motion. Simple harmonic motion. What does it mean? The solution will be what?
Some constant e to the.
Will be cosine and sine. And this is an eigenvalue problem. The solutions will be cosine and sine, and it will have the harmonics. So cosine x, cosine 1x, 2x, 3x, whatever, nx. It's like the Fourier analysis of Fourier series. When you write a function in terms of the Fourier series, those components of the Fourier series, a naught, when you write Fourier series, like f of x, you write it as summation of a naught from I equal to, let's say, you write it a naught plus summation of ai cosine, let's say, cosine x plus b naught plus summation of I bi sine x. And I goes from 1 to infinity, and you will have the Fourier decomposition for any function. So again, for the eigenvalue problem, I can expand my, let's say, function, any function of the components of the eigenvectors. For this cosine and sine, what are the eigenvectors? The cosine and sine are the eigenvectors. So I can expand any function in terms of the harmonics, which are cosine and sine and so on. So we will try to solve the same. So the solution of this equation for the simple harmonic motion is psi equal to what? A cosine the square root of b multiplied by what? X plus c sine bx. And in order to have a situation like this, you expect there is a fissile material inside the medium, and you expect the flux to have what shape in a slab like this? You expect that you will have neutron generation everywhere in the slab. Yes, guys? But the neutron generated near to the borders will do what? Will escape. Yes? So I expect that I will have less neutrons when I move from the center to the what? To both sides. So I expect symmetrical what? Variation. So this symmetrical variation will give me a cosine function which is symmetric in the center, and it has maximum in the center and zeros in the what? In the border. But because of the diffusion equation, I told you last time that usually we have our mathematical way to treat the diffusion equation is not to make the flux zero on the border so that we do not have discontinuity for the flux and this validate or negate the diffusion equation, so we have to make it equal to zero at some extrapolated distance. So here, this will entail that C is equal to what? Zero, because the sine function is not symmetric here. Of course, if you move and you make your coordinates here, so the zero is here and this is 2a instead. Now I can use what? A sine function, because the sine will have 0 at 0, and at 2a or half the period it's 0 again. Yes, guys? So it depends on where you put your origin. If we put the origin in the middle, the symmetric case in this case will be the cosine. If you put the 0 here, the symmetric case will be what? Sine. So now this will be our equation. But what is the boundary condition? Phi at a extrapolated plus or minus equal to what? Equal to 0. So this will lead to what? By the way, we will call this a. So the whole distance is a. So this will be a extrapolated over what? Over 2. And this will be minus a extrapolated over 2. So make it over 2 so that I will be consistent with the book. So the whole distance is what, guys? The whole distance is A extrapolated. So it is A extrapolated over 2. So when I apply this will give me what? This will give me A multiplied by cosine B, and X is A extrapolated over 2. So two things multiplied by each other equal to 0. So either A is equal to 0 or the cosine is equal to 0. But I cannot get A equal to 0. Why? Because I already make C equal to 0, and if I make A equal to 0, the flux will be the trivial solution, and I will have what? 0. So it is B, the cosine of BAX over 2 is the one that is equal to what? 0. So in this case, cosine BA extrapolated over 2 is equal to 0. And when the cosine will be equal to 0? When this term here, BA extrapolated over 2, will be equal to multiples of bi over 2. Yes, but not a whole multiple. It's an odd multiple. Because if you have 2 bi over 2, this will give you what? Bi, and cosine bi is not 0. So you have to have odd multiple of bi over 2. So this will give me what? N bi over 2. We can write it 2n plus 1 like last time, but no, I can write it n bi over 2, and I will restrict n to be what? Odd. To be odd number, 1, 3, 5, 7, and so on. Last time I put, if you remember last time, I put n to be what? 2n plus 1, and I ran n over what? All integers, 0 up to infinity. Now I will just put 2n bi over 2, and I will restrict n to be what? Only odd numbers. Guys, did you follow up what I am doing? If you do not understand, please let me know. I do not want this to drag until the end of the semester, and then this will be a disaster. So please stop me if you do not understand anything. I will be more than happy to pause and help you. Yes?
You're saying that B times A extrapolated over 2 is equal to n pi over 2. Now, A extrapolated, did we put that in for our x? Are we only saying that B is equal to n pi?
Okay, so the condition here is when x equal to A extrapolated over 2, the flux equal to 0.
Right.
So you will substitute in this equation.
Okay.
Phi equal to 0, so this will be 0 multiplied by A cosine B, and at what value is equal to 0? At x equal to A extrapolated over 2. Right. So this is the condition here.
Okay. All right.
Guys, did you understand? Okay, so what's B now?
In the Bible,
Bi will be what? N bi over A extrapolated. Again, it's not good to leave it as B. So I have to give it what? N. Because now B is a function of N. There is B1, B2, B3, B4, of course. But of course B1, B3, B5, and so on. Yes, guys? So what's B square? B square will be what? N bi over A extrapolated all square. So B is what? Yes, go ahead.
Where'd your 2 go? Oh, okay.
2 will cancel. B is what? In my equation. My equation was nabla square psi equal to what? So what's B?
the eigenvalue.
Eigenvalues. So actually, we got the eigen what? The eigenvalues of the problem. Now we want to calculate what?
Eigenfunctions.
The eigenfunctions. So my eigenfunctions now, psi n, I call it psi n of x, will be the summation of what? An cosine Bn x. Yes, guys? Yes, because I no longer have only one value. So psi of x was equal to A cosine Bx. but I no longer have only one value for a B. So I have B, which one? B1 or B3 or B5 or B7 or whatever. So this is like exactly like what? Like this, when you do Fourier analysis. You will write your function as A naught plus cosine summation of AI cosine X and so on. Yes, go ahead.
Is there a function for an?
Huh?
Is there a function for an, just like there's one for bn?
No, this is just the constant, but because the constants, you have constants, like A naught, A1, A2, A3, A4, A5, there is constant. Okay, if you have a solution for a differential equation, everybody sees here? If you have a differential equation like d2y squared by dx squared plus ay equal to q of x, if y1 is a solution and y2 is another solution, so y equal to a y1 plus b y2 is also a solution. So any linear combination of the solutions will be what? A solution. So I have cosine bx at the very early beginning was what? A solution. But b1, cosine b1 will be what? A solution. And cosine b2, a solution. That will fulfill that the flux at the A extrapolated equal to what? 0. And b3, cosine b3 is another solution. So any linear combination of those solutions will be what? A solution. Where is the linear combination? Here it is. It's a1 cosine 1x plus a2 cosine 2x plus a3 cosine 3x plus a4 cosine 4x and so on. So this is like exactly the same like this. I'm making the linear combination of the individual eigen functions to be what? To be a solution. Did you understand this? Okay guys, so now this is a solution. Now if we return back to our equation, the equation V over psi multiplied by D nabla square psi plus nu sigma fission minus sigma absorption multiplied by psi is equal to negative lambda. This is the original equation. You remember this one? I just wrote this one before we solve the eigenvalue problem. Yes? This was the x component of the partial differential equation. So now let's look at this equation. So we agreed that, okay, if I look at the first harmonic, so a equal to 1 and n equal to 1, so this would be cosine what? Cosine b1x. Yes, the first harmonic is a solution to the problem. Yes, second harmonic is a solution to the problem, third harmonic is a solution to the problem, and so on, and the linear combination of those harmonics will be also a solution to the problem. So if I look at the first harmonic and I just substituted in the equation over there, this will give me, and I multiply the equation over there, I multiply the two sides by psi. So if you multiply the two sides by psi and you substitute with the value of psi, you will get V minus nabla square a1 cosine b1x, let's say, minus nu sigma fission minus sigma absorption multiplied by a1 cosine. Let's say that I will keep the bn's. Okay, and this will equal to, I multiply also by minus sign, so this is equal to lambda n a1 cosine b n multiplied by x. So if you try to just evaluate nabla square, so what's nabla square? A1 is constant, will go outside, and nabla square, just you will differentiate this twice. So when you will differentiate it twice, you will obtain what? B square n. Yes guys? Yes, b square n multiplied by cosine bn. cosine Bn will cancel with cosine Bn, will cancel with cosine Bn, and you will end up with this function. Lambda n equal to sigma absorption plus dB square n minus mu sigma fission.
Dr. Abdul,
Yes.
where'd your D go in that second equation there?
Which one?
The one that's supposed to be a, should there be a D there?
Yeah, it should be D. Thank you. Okay, guys? Do you have any questions so far? So, what's the final solution then? Phi of x and t will be just psi of x multiplied by what? T of sine t. And this will be what? Summation for n odd, meaning 1, 3, 5, and so on, an t naught e to the power of minus lambda n t cosine bn is just n multiplied by pi divided by a extrapolated, all multiplied by x. So this is the final solution for the eigenvalue problem. How to get the constants? This is, by the way, this is very typical problems. You will find it not only in neutronics, but you will find it in heat transfer, you will find it in fluid mechanics, you will find it everywhere. Eigenvalue problem, Laplace square multiplied by a function phi or whatever you name it, Laplace square y equal to lambda square or lambda y. This is exactly how you will solve it. You will say, okay, I'm solving in 1 dimension, 2 dimension, 3 dimension, Cartesian, okay, I have boundary condition, I have initial conditions, and you solve it and you get the eigenvalues and eigenvectors. Finally you reach to here. Then you will have one remaining constant to calculate, which is an. How to calculate an? Usually we calculate an from the initial, of course, the initial condition at t equal to 0. This will be equal to what? 1, and I have phi naught of x equal to summation over n odd an cosine n by over a extrapolated multiplied by x. So now I can calculate this from something called orthogonality property. Orthogonality property. What does it mean? We knew that for the Fourier series, what are the eigenfunctions? Sine and cosine. Sine and what? And cosine. So those functions, usually for the eigenvalue problem, your eigenfunctions or eigenvectors, they will be orthogonal. What does it mean, orthogonal? It means that if you multiply psi, let's say psi of x n multiplied by psi of x m, and you differentiate over the whole space from x equal to negative infinity to plus infinity, this will give you half the period if n equal to m. So if n equal to m, this will give you half the period that you are integrating. Here, of course, we'll see the period in cosine and sine will be just the periodic length. And it will give you 0 when n not equal to what? M. This is called orthogonality. What does it mean, orthogonality? They are orthogonal, perpendicular to each other. So the sine and cosine, they are shifted by 90 degrees. They are orthogonal. Okay, the sine and cosine. So if you integrate the sine, let's say sine and cosine, So when n equal 1 and n equal 2, for example, this will give you sine and cosine. You integrate over a period, you will get half the period, half a. Okay, if n equal m, but if n is not equal to m, this will give you what? 0. And this is what we will see here. So to do this, so what we will do is we'll multiply this equation. We'll multiply this equation by cosine m by over a extrapolated x, both sides, and then integrate like here. So when you do this and you integrate, you will notice that when cosine, and you can go and try it yourself, you will notice that we will integrate from minus a over 2 to a over 2, because our slab is what? The full period of the slab or the half period of the slab is what? Is a. Yes? So I have to integrate from minus a over 2 to plus a over 2, and this will give me phi naught cosine m by x over a extrapolated, and I will differentiate to integrate to delta x. So you multiply it, phi naught of x, you multiply it by cosine m by x a ex, and then the other side you will integrate from what? Negative a over 2 to a over 2, and then you will have the summation sign here. Okay guys, and then you will have an cosine n by over a extrapolated x cosine m by x a extrapolated dx. Okay guys, and n is odd. Is odd.
Does m have a similar restriction, or is it just all?
What do you say?
Is m also restricted to be odd, or all real numbers?
Yeah, but both of them should be odd. N and m should be odd. If you want to believe me, just run cosine x, and here is n, and here is m, multiplied by cosine mx dx, and just make it from negative a over 2 to plus a over 2. If you want to believe me, when n equal m equal 1, so this will be what? Cosine square what? Cosine square x dx. So this is even or odd function? Any function you square it is even. An even function you make it from negative a over 2 to a over 2 is equal to the integration from 0 to a over 2 for the same cosine square. And if you have the cosine is like what? Like this. When you square it, what you do? Just bring this from negative to positive. So and you double it. Yes? So this will be like this, then like this. Yes? Yes guys? So when you integrate this, it will give you number. Yes? Now, when n is not equal to m, so let's assume that n is equal to 1 and m is equal to 2. So I will have what? Cosine x multiplied by cosine 2x. Now this is not an odd function. You will notice that this is not an even function. You will notice that this is a function, odd function. So what you want to do is to do what? Just make the trigonometric decomposition for cosine 2x. So cosine 2x is cosine x plus x, and cosine x plus x is what? Cosine minus sine. Then you will evaluate this over the period. You will notice that this will give you 0. Okay guys, just the test. Go ahead today and try it using even calculator, and write cosine x and cosine 2x and integrate from negative a over 2 to plus a over 2. It will give you 0. Okay guys, but when m equal to m, this is an even function. You integrate from a period, because it's an even, it is twice the integration from 0 to the period. Okay guys, so this is exactly what you will do here. So this will give you what? Because you have summation, if n equal to m, this will give me half the period. So what's the period? A over 2 plus A over 2 is A. Half of it is what?
A over 2.
A over 2. And when n is not equal to m, will give me what? 0. So the summation will be gone, and I will only remain with the situation where n equal to m. So this will give me what? Give me 0 when m does not equal to n, and will give me A over 2 when n equal to m. So now, what's the right hand side? What's the right hand side, guys? The one that I was looking for? This one. Yes? So when you evaluate the right hand side, cosine m by x over a ex dx, if you notice constant will get out, and then you will get from this, you will get the integration is an, then you will get the value of an and divide. This will give you 2 over a extrapolated multiplied by negative a extrapolated over 2 multiplied by a extrapolated over 2 phi naught of x cosine m by x over a x dx. So from here, if m equal to n, this will give you 0. If n equal not equal to m, will give you 0. If n equal to m, will give you a over 2. So this as a whole will give you an multiplied by a extrapolated over 2. So an will be this multiplied by 2 over a extrapolated. And this is what I wrote here. So this is how to get the what? The constant. So now you finally define everything. You define the solution for the flux, and you define the constant for the flux. Okay, guys? So do you have 2 more minutes, or do you want to leave? I do not want, because if I wait until the next time, it might be difficult to start over and show you the last thing. So if you look at the solution now, you will notice that your solution is cosine multiplied by exponential function. Yes, guys? So, but I have a summation of cosines. I have a summation of what? Cosine. When cosine bx, when bn equal to 1, so this will be what? b1. Okay? And when you look for 1, this will be just pi over a extrapolated. When this is 1, this will be pi over a extrapolated multiplied by x. When you plot this function, you will, let's assume that the flux goes 0 at the border. So this will give you what? The solution. When you look at n equal to 3, this will give you something like this. Okay, guys? When you look for, let's say, 5, this will give you something like this, and so on. So those are the harmonics. Does it mean anything, those harmonics? From the physical point of view, do you think the flux will go negative inside the medium?
No.
So the only important term will be what? The first harmonic. And why? Because if you look here, when n grow, what will happen for this one? Well, with time, it will decay away. It will wash away. So if we assume that we have a reactor at certain power, B naught, and then I remove the control rods from the reactor to increase the power, what will happen? The flux will have several harmonics. All of them will die away, except what? Except the smallest n. And the smallest n is the what? Is the first harmonic. So the first harmonic will be like this. Then when you increase the power, what will happen? The flux will increase. Or if you decrease the power, the flux will do what? The flux will decrease. But I will keep the same shape of the flux. I will keep same shape of the flux. Although there is some transitional period where you will have those harmonics, and with time those harmonics will die away. So you will notice that B1 square is less than B3 square, less than B5 square, less than Bn square, and you knew that lambda 1 is less than lambda 3, less than lambda 5, less than lambda n, and you knew this. So we will have the final flux as a function of x of t will be just a1 e to the power of minus lambda 1 t multiplied by cosine b1 x. So this will be just the form and the shape of the flux with time and with space. Next time we'll continue. Do you have any question? Yes.
So you're saying at startup, we might see these higher order harmonic curves.
Yes. Not startup, at transition, if the flux is constant.
So when a transient is significant, then that's when we see the higher order.
Let's say when you have a transition from a steady state, you will start to see those harmonic, but they will die away very fast.
Right.
And you will end up with the first harmonic, which is the flux.
Of course.
Guys, do you have anything, any question? Okay, have a wonderful time and see you next time.